I hope you had a wonderful spring break and a very happy Mother's Day. We only have 2 more weeks to study the physics of light before jumping into our next unit, which I'm super excited about. So, before we dive into today's experiment, we are going to play a quick review game with Pi so we can remember all of our past experiments and all of our past rules and vocabulary that we have come up with during our physics of light unit. So, let's get Pi out here to play a game called Which Experiment Was That? Pi, are you around? Are you around, Pi? Ah, there you are, Pi. Okay, are you ready to play Which Experiment Was That? Okay, so why don't you grab a rule and we will guess which experiment that was. Okay, rule number 1 from all the way back in March was that objects can only be seen when there is light shining directly on them. Do you remember which experiment that was? Oh yes, Pi, that was a very simple experiment. That was our first one where we simply observed objects that had a lot of light energy shining on them and less light energy shining on them. And obviously you can see me really well right now because I have a lot of light energy shining on me. So there's lots of light energy bouncing off or reflecting off of me. But if there's less light energy, colors appear dimmer because there is less light energy being reflected. Of course, if there is no light energy at all, we cannot see anything. For example, in a dark cave or a dark room, you would not be able to see anything because there's no light energy for you to see. Okay, let's play round number 2 with rule number 2. Why don't you grab rule number 2, Pi? Rule number 2 was that light travels in a straight line until it hits an object. Which experiment was that? Do you remember, Pi? Ah, yes, that was from our experiment when we were exploring shadows with opaque, translucent, and transparent objects. We learned that opaque objects create shadows because the light cannot pass through them, and the shadow is basically the part where there is no light shining and the light is blocked. Translucent objects can also form shadows, but the shadows are not as dark because some, but not all of the light can pass through that object. Does that make sense? Remember that? Okay, let's do round number 3 with rule number 3 of which experiment was that? Rule number 3 was that light slows down and refracts when it crosses the boundary between 2 transparent medium. Which experiment was that? Do you remember, Pi? Ooh, we did a bunch of experiments with refraction. That is true. So we can just remember that the reason some objects look bigger in water than they do in air is because of refraction. And the reason we see rainbows is because the light is refracting. All of those different wavelengths of light refract at slightly different angles, causing rainbows to form. And we did some other refraction magic tricks as well because the light is bending. Moral of the story, refraction means to bend. Okay, Pi, are you ready for rule number 4? Okay, rule number 4 that we came up with was that when light bounces off of a perfectly smooth surface, a reflection is made. Which experiment was that? Ah, yes, Pi. That was when we were experimenting with our mirror. We learned that we can see a reflection in our mirror because at a microscopic level, it's perfectly smooth. So all of the photons that are coming in and reflecting off of that surface stay in the exact same order. We compared that with our control, our piece of paper. Can you grab the piece of paper, Pi? There we go, with our piece of paper. And actually, the main thing that these 2 objects have in common is that they're both reflecting all of the light that is shining on them. But the photons stay in the same order with the mirror, but they mix up and become white again with the white piece of paper because the white piece of paper is actually bumpy at a microscopic level. So all of the different colors of light, all the different colors in our visible spectrum recombine, and that's why we see it as white. Because last week we learned that white light is made up of all of the colors in the visible spectrum. So that means that my lab coat is reflecting every single spectrum of light and it is absorbing no light, which brings us to our first new vocabulary word for today. The opposite of reflect is, do you know, Pi? When we're talking about physics of light, it's not refract. The opposite of reflect is absorb. So some wavelengths of light, instead of being reflected and looking white, they are absorbed. So let me see. To help illustrate this, let's imagine instead of wearing my white lab coat that's reflecting every single color of light, what if I was just wearing my turtleneck? So my turtleneck is the color black. We already learned in our very first lesson that black is the absence of color. So if you are seeing something as black, that means you are not seeing any light reflecting off of that surface. So if the light isn't reflecting, where does it go? That light gets absorbed. If something looks black, that means that every single color in the visible spectrum is being absorbed and you cannot see any color at all. So what I would like you to do is either right now or after this video, copy down the definition of absorb into your science notebook or any notebook that you have been using for this unit. The definition of absorb is to take in or soak up energy, liquid, or another substance. So again, you can pause the video and copy this down right now, but this definition is also available in the Google Doc. So if you want to watch this video to the end and then copy down the definition directly from the Google Doc, along with some other very helpful supporting diagrams, you may choose to do that instead. Okay, so we know that things that appear white are reflecting every single color in the visible spectrum and absorbing no colors in the visible spectrum. The color black is the opposite. We know now that it is absorbing every single color in the visible spectrum and reflecting back no colors in the visible spectrum. But what if I was wearing a red jacket? Okay, so if something appears red, why does it appear red? Well, let's think about the white light that's shining, right? So we know that the white light shining down on this jacket right now contains every single color in the rainbow. Red, orange, yellow, green, blue, indigo, and violet. But all materials have a property called selective absorption. Absorption. So selective means that it's selecting just particular colors that it likes to absorb, and then it reflects the rest. So, for example, my red jacket is selecting to absorb all of the colors except red. So it's reflecting red, and then it's absorbing orange, yellow, green, blue, indigo, and violet. The only color being reflected is the only color that you can see. So, what I would like you to do is either copy down the definition of selective absorption now, or same thing with the last word. It is also available in the Google Doc on Google Classroom with some extra supporting diagrams and some extra information, and you can copy that down into your notebook from there instead. But the definition, I'll leave it up for a second and you can pause it, is the tendency of an object to absorb some frequencies of light more than others. Okay, so before going on to our next video, please make sure that you have copied down the definition of absorb and selective absorption into your science notebook. It is available in this video. If you go back and hit pause, it is also available with more information and diagrams in the Google Doc, in Google Classroom. And of course, if you feel like you missed any information that's super important from this video, you can of course replay it and listen to me explain it again so you are super prepared to dive into our next experiment. And I will meet you with Pi in the next video. Bye.